Okay, guys, good morning. How are you today? Can you all hear me and see the slides? Good, Michael, thank you. I'm fine. Have you all finalized the Spark Plus for assessment one? I just can see some students haven't completed yet, so I have extended the due date until tomorrow. Last day will be tomorrow. I can see 8 students have not completed it yet, so hopefully by tomorrow everyone complete it. Okay. And do you have any question before we start, guys? Rolin, Michael, Rahmat, Wanyu. Any question? Okay, that's good. So today will be our week 11 lecture, and actually this is our last lecture of new topics, and next week we will have revision. So today our lecture will be about the design of columns and beam column members. So last week we finalized the beam, or we go through the beam design or member under bending moment. Today we will design member under axial load and combined axial and bending moments. Okay? Okay, so let's start our lecture. So we're still continuing in designing of the cold formed steel members, and today topic will be about columns. Columns means member under axial load only. Beam column members means member under axial loads and bending moments. Okay, so this lecture will help you to design the column of the shed in project 2. And here is some example of the columns we looking at. So as you can see, this building is from cold formed steel, and as you can see, here is our column of the shed, and this is one is a beam column member, because this column, what you expect, it is under axial load N asterisk and also M asterisk. So in frames, most of the columns are under axial load and bending moment, cannot be under axial load only. Okay, and here is the, as you can see, the columns or beam columns. Beam column is just a definition that it has N and it is under M and M. N and M. And here is the rafter we have designed last week. And here is, what is this, guys? Do you know? These members are purlins. Okay, and as you can see here, we have the diagonal members, which are the bracing. Okay, and if I ask you, what is this member here or here? Do you know? Merlin, yeah. Thanks, Michael. So, and as you can see here, it is a little bit unclear, but this is wall bracing. So these are the members we may have in a shed, a cold formed steel shed, and these are the members you will need to design in project 2. But our target today our job today is to design beam column member under bending moment and axial load. Okay, so let's start with the columns first. Columns here means member under concentrically loaded compression member. So if we have a column from cold formed steel, so we have axial, the center or CG of this member, and sorry, let's make it to be easier, because if we apply the load here, it will not be concentric. So if we have columns without any bending moment. So this column, for example, if we have double channel like this, so where is the neutral X or where is the CG? Here is our CG. So this section is two channel back to back, for example. So this is our CG here. This is X-axis, for example, this is Y-axis. So concentrically loaded column, what it mean? This means that we have load acting here. So N, we have only N asterisk acting in here. So this one is column under or subject to concentric loads. Okay, for the columns under this or the section under concentrically loaded axial compression, we have four type of section. We have double symmetric section. Double symmetric section means it is symmetric at about x-axis and y-axis. Single symmetric section means only symmetric about x or y-axis. So doubly symmetric, similar to here. So here is a doubly symmetric section. Single symmetric section means only symmetric about one axis, similar to something like this, for example. Only one channel. If we have one channel, so the channel is symmetric only about x in this case, for example. So this is singly symmetric. And we can have buoyant symmetric section, so it is symmetric about one point, or random or general section, which is non-symmetric section. So four type of section, we can see these four types here. So these are the type of section we can have in columns of cold formed steel structures. So the first one here is example of doubly symmetric section, which include any hollow section like rectangular hollow section or square hollow section or circular hollow section, because they are symmetric about x and y. So symmetric about x axis and y axis. And or it can be double channel like this one or this one. So double channel, lipped or unlipped channel. So this one unlipped. And this one is lipped channels. Okay, because why we need to know the section or the cross section symmetric or single symmetric or non-symmetric, because this will affect our procedure or our formulas like related to buckling, local buckling, or member or global buckling. The other type which is the single symmetric, similar to this one here. So it can be one channel or C-section, C-section lipped, and this one C-section or head section This one two angle, two equal angle. This one is angle, but taking 45-degree orientation and with ellipse. So all these are example of the single symmetric section. Point symmetric section, like this one here. Point symmetric section, like Z section here. So Z section, we have unlibbed Z and libbed Z, or this cross section, or the plus section, which is symmetric about this point here. So this section are symmetric about this point. So we have the Z mainly in our calculation. Z is point symmetric. Single channel is singly symmetric. Double channel is doubly symmetric. Or the last one is non-symmetric section. Non-symmetric section means, or we can see that there is no symmetry about any point or axis, like angles. So this one is unlibbed angle, and this one is a libbed angle. Okay, so these are the example or the shapes of the section available in the market, and let's now go to the design considerations for member under or columns under axial loads or axial compression. So for member under axial compression, as you know, or as we discussed earlier, what is the problem we have with axial compression, guys? Do you have any idea? Our problem is what? Buckling. So the main problem we have is buckling. We have two type of buckling, which included in member behavior and element behavior. For member behavior, we can call it overall behavior or overall behavior of the member, which include the yielding for short or compact members, or our main problem is the overall buckling. So our main problem in axial compression members is buckling. We have two type of buckling, which is overall buckling. In columns, we have three types of buckling. One, two, three. We have flexural buckling, which means bending about one of the principal axes, X or Y. Torsional buckling means twisting about the shear center. Torsional flexure buckling, which means combination of the first two, or simultaneous bending and twisting. So torsional flexure buckling will include bending about one of the axes plus twisting about the shear center. So these are the type of overall buckling we have in members under axial compression. Another behavior we need to discuss or we need to consider in our design, which is the element behavior or local behavior or local buckling behavior. Local buckling behavior, which means buckling or local buckling of the individual element within the cross section, means we may have in this our channel like this, we may have buckling in the whip or buckling in the flange. So this is local buckling behavior. So similar to hot rolled steel, we are worried or we are concerned about the local buckling behavior and global buckling behavior for member under compression. And here is some example. This is the finite element modeling results for members, doubly symmetric members under axial compression. And here is the buckling modes. Buckling modes means how the buckling will look like when we apply the load. So as you can see, here is some or four modes of failure for this doubly symmetric column. So this one, mode 1, for example, mode 2, mode 3, mode number 4. So each one of these modes can reflect one of these buckling behavior. So one considering or one for the flexure buckling, one for the torsional buckling, one for the torsional flexure buckling, and one for local buckling. Okay, so here are the modes. These modes are using finite element modeling using Space Gas or Student 7 or any other software. And here, as you can see, this is the Euler load or buckling load for buckling about X axis, sorry, Y axis. And this one is the Euler or buckling load for buckling about X axis. Okay, so as you may study before or as you know, the buckling or the critical buckling load BCR is equal to pi squared E I divided by L effective square. So BCR is the critical buckling load, or we call it Euler load. So Euler load or critical buckling load is the load when column initiate or start the buckling. Okay, where E is Young's modulus and I, what is I? I is the moment of inertia about the axis we study, the axis under analysis. So if you are studying buckling about X, so IX. If you are studying buckling about Y, so IY. L effective is what? LE is the effective or buckling length of the column. Do you know the formula of buckling length? We have studied before. LE is equal to what? K times L. L is the length, and what is K? K is buckling coefficient depend on the column ends. Okay, so this buckling modes and the buckling loads are depending on the length of the column, the cross-section dimension of the column, the end condition of the column. As you can see in the model here, on the model, we have some orange parts or orange nodes. These orange nodes are the boundary condition or the restraint of the column. Okay, so all these are elements affect the buckling modes and buckling shape of the column. Okay, let's keep this in mind. Now let's have a look on buckling modes for columns that are singly symmetric about x-axis. So we need to know or have a look to compare the buckling modes of this column. So as you can see, here is the column we have. It is only a C section column, lib C section. So this lib C section is column only symmetric about x-axis. So here is the buckling modes. Buckling mode 1, 2, 3, 4. So as you can see, due to the shape or the section, the cross section geometry. So we have different buckling modes compared to the previous one, but still have the first one is local buckling, and these three are for global buckling. Okay, one of them again for flexure, one of them for torsional, one of them a combination of of torsion and flexure. So again here the buckling in the overall buckling includes these three modes: flexure buckling, torsional buckling, and torsional flexural buckling. Okay, do you have any question up to here, guys? Okay, so now let's go through how to design the columns under flexure, sorry, under axial load. And this section is covered in the Stern standard AS 4600, section 3.4. So, design of concentrically loaded compression members. So, if we have a look on the standard here, so here is the standard. So, similar to hot rolled steel, we have N asterisk the applied in a normal force, and we need to compare to the section capacity and member capacity of the member. So the concepts of cold form steel design and hot rolled steel design are quite similar. The difference is just the parameters or formula due to the probabilities and different nature of the thin walled and the cold formed steel and the hot rolled steel. Okay, so let's go through the formulas. These formulas are extracted from the standard, as you can see. So for concentrically loaded compression member means we don't have bending moment on this column. So axial only. Axial only means we have only N asterisk. So we need to check N asterisk less than or equal to phi CNS, which is the section capacity, and N asterisk less than phi CNC or the member capacity. Okay, where phi C is the capacity reduction factor for members in compression, table 1.6.3. If we go to the standard quickly to get an idea how much is phi C from table 1.6.3. So here is our table. For members subject to or concentrically loaded compression members. How much is phi? 80.85. So if we go back to our slides, so phi in this case is 0.85 for axial loaded compression member. NS, what is NS? NS is the nominal section capacity of the member in compression. NS will be equal to A effective phi Y. So N asterisk, NS is equal to A effective Fy. Fy is F yield. So Fy is yield strength 500 or whatever the value. So 450, 500 based on the grade of the steel. A effective is the effective area at yield strength. This comes from the capacity tables. And for NC, what is NC? NC is the nominal member capacity, which equal to AE times Fn, where AE here is not effective area at yield stress. It is effective area at critical stress. So AE here, not from the table. We need to calculate AE. Okay. Fn is the critical stress as well. So for the member, for the section capacity, it is a simple step. So you just need to find, A effective from table and multiply by Fy, you will find NS. The problem or the effort will be to find NC, which is E effective at stress Fn, and we need to find Fn. We will see now how to find them, but let's go to Fn. Fn is the critical stress and shall be determined from equation 3.3 or 4 as appropriate according to what? Lambda C. So actually we have two cases for Fn according to the factor lambda. So Fn depend firstly on lambda C. Okay, if lambda C less than 1.5, so you will need to use this formula here. Fn equal to 0.658 to the power lambda C squared multiplied by F yield. Or if lambda C more than 1.5, Fn, the critical stress, is equal to 0.877 divided by lambda C squared F yield. Okay, this critical stress can be due to the flexural buckling case, or what is the second case, if you remember here? Torsional buckling or torsional flexural buckling. So the critical stress will be the most critical stress from this three: flexural buckling or torsional buckling stress or flexural torsional buckling. So it is like we have three cases and we will pick the critical the critical from the three. Okay, so to select a value or to find the value of Fn, we need first to find lambda C. So firstly, we need to find lambda C. How can we find lambda C, guys, here? Using this formula here. And what is lambda C? Lambda C is non-dimensional slenderness ratio to find Fn. So lambda in our calculation of cold formed steel all the time, it is slenderness ratio. So as you can see here, lambda C is equal to root F yield divided by FOC. F yield is the yield strength, so FOC is what we need. FOC, as we mentioned earlier, is the list or the critical of the flexural, torsional, and flexural torsional buckling stresses. These stresses are determined using paragraph D1.1, appendix D. Have you seen something like this before in last week? We have something like this for member under flexure. We have FOX, FOY, and FOD. So all these critical stresses need to be found to find the slenderness ratio, and then using the slenderness ratio, you can find the allowable or the required Fn or Fd or whatever in compression member or tension member, sorry, in compression member or in member under flexure. Okay, if we go to the standard here, so let's have a look on section D. So can you see section D now? So here for section D, here is the formula for FOC. FOC for doubly symmetric section or closed section and any other section that can be shown not subject to torsional or flexure torsional buckling. The elastic flexure buckling stress equal to this formula here. FOC divided by E by squared E divided by L effective over R. So this case only if we don't have torsional or flexural buckling uh, stresses here. This means that this case only for flexural buckling. Okay, so if we go back to our slide. So for the elastic buckling stress or flexural buckling, this is the first possible failure mode. The elastic flexural buckling stress is determined using the following formula. FOC equal to pi squared E divided by L effective over R. This is closed number D 1.1.11. Okay, in this case, as we see in the lecture, the standard, no torsional or flexural torsional buckling happen. So if you have the appropriate restraint to prevent torsional buckling and flexural torsional buckling, so your FOC will be using this formula here. Okay, this is illustrated in this example here. So in this case here, we have the proper restraint to prevent the torsional and flexural torsional buckling. So this is our formula, and our expected mode of buckling is only flexural buckling mode. Okay, where L effective, as you can see here, L effective in the formula is equal to K times L. We have discussed this earlier here. So L effective is the buckling or effective buckling length. It is equal to K times L. So this is the first case, the elastic buckling or elastic flexural buckling stress, FOC. The second case or the second failure mode is the torsional buckling. Torsional buckling, as you can see here. So we have twisting of the column about. Do you know what is the axis of twisting here? Is it twisted about x-axis or y-axis or z-axis? Anyone have idea? Okay, so the buckling will happen or the twisting about z-axis. So this is z-axis because this is our x-axis, this is y-axis. So usually the twisting happen or around z-axis. So the torsional buckling, one of the possible failure modes, and the torsional buckling stress using the formula below, FOZ, because it is buckling about z-axis, equal to GJ divided by A RO1 or RO01 or RO1 squared multiplied by 1 plus pi squared EIW divided by GJL effective EZ, where G is what? G is the shear modulus, J is the polar moment of inertia. Where to find the polar moment of inertia? From the tables. A is the gross sectional area. RO1 is what? Polar radius of gyration to the shear center. E, Young's modulus. IW is I warping or warping parameter. G again, J again. L effective Z is the buckling length about Z axis or the Z axis. Okay, so let's go to the standard again to see where is this formula. So here is the formula. FOZ, the elastic buckling stress, and here is the formula of the buckling stress for torsional buckling mode. So here, this formula is close G point one point one or sorry D1 D1.1.15. So now up to now we have two cases of if uh, or the buckling stress. So we will need to, if we expect all failure modes to happen, so we need to find all of the stresses and then select the least or the most critical one, which would be the least of the three. This one here is the third mode of failure. So what is the third mode of failure? As you can see here, torsional flexural buckling mode. This also one of the possible failure mode in this case. One of the failure mode we expect. So we need to calculate this one as a third failure mode. And here is in this diagram here to the right is have the torsional buckling means, or what is the torsional buckling means. In this case, means we have a combination of twisting and bending about one of the principal axes. So as you can see here, the member bent about y-axis. What else? During the bending, we have also twisting about z-axis. So we have torsional or twisting about z-axis along with flexure or bending about y-axis. Okay, so this mode is the torsional flexural buckling mode, and the elastic buckling mode in this case will be, or the elastic torsional flexure buckling stress in this case will be determined using the formula FOC equal to 1 divided by 2 beta multiplied by FOX plus FOZ all squared minus FOX plus FOZ all squared under the root minus 4 beta FOX FOZ, and beta in this case is 1 minus XO divided by RO1 all squared. Or conservatively, we can find FOC in this case using this formula here. So this is the accurate or exact one. This is approximate or conservative value of it. Okay, so this is the most like complicated one because it has combination of the first two. So if we go to the standard here, here is the formula for doubly or singly reinforced section, symmetric section, sorry, doubly or singly symmetric sections subject to torsional or flexural buckling. The stress will be FOXZ 1 over 2 beta FOX plus FOZ minus FOX FOZ minus 4 beta FOX FOZ, where FOX is the flexure one, FOZ is the torsional one. So it is a combination between the two. If you don't have time to do this, or if you want a conservative estimation of it, so we can replace the formula here, the complicated formula here, with close D118. Okay, so if we go back to our slide, so this clause here is clause D1.1.12, and this clause here is D1.1.18. So, in summary, we will have three stresses for the critical stress FOC. One of them using this formula here, D1111, and one for the torsional buckling here, which is clause D1115, and one for the flexural torsional buckling, which is D1112. So our FOC will be the least of these three. If you have the three cases of failure or the three modes of failure, so we need to find the three stresses, and FOC will be the least of them. Then, so this one will be least of three FOX, FOZ, and FOXZ. Okay, then after we know FOC, we can know lambda C. If we know lambda C, we can know Fn. If we know Fn, we can find AN. Fn here, we can find A effective as well, so we can find NC. So our problem or our efforts in designing the concentrically loaded member will be the value of Fn, because we will need to find FOC. FOC is three cases. The three cases are flexure buckling, torsional buckling, and torsional flexural buckling. Okay, do you have any question up to here, guys, for this one? Let's quickly have a look on this one for non-symmetric section. So the first part was for the symmetric singly or doubly symmetric. For non-symmetric section, which we might not face in our course here, but just for information. Non-symmetric open shapes that have no symmetry, like angles, either about x or a point, either about axis or a point, FOC shall be determined from testing. Okay, so for non-symmetric section, it will be hard to find the stress using formulas, so we need to do some testing. Also for columns with flange through or fastening through the sheeting, we will have different criteria to design. Do you know what columns are fastened to sheeting? Do you have idea what columns may be fastened to sheeting? No? So if we have a column in a wall and the wall sheeting is fastened directly to the column, so the buckling of this column will be different. The buckling behavior of this one will be different. This one option. Another option is purlins or girts that are under axial load or combined axial load, so this formula can be used. So if you look to this clause here, 3.43, column with one flange through fastened to sheeting. So here the member capacity will be using this formula in clause 3.4.3. NC equal to 0.79 S plus 0.54 multiplied by 0.046 T plus 0.93 multiplied by 0.1 BF minus 0.064 D plus 2228 to 22.8 multiplied by EA gross divided by 29,500. So will have in this case direct formula if we have weak axis. So the nominal member capacity in axial compression of simple span or continuous channel shall be determined from the following equation. For strong axis, we don't have a problem, so we can use the previous formulas. But for the weak axis behavior, so we need this formula here, where S is the fastener distance from the center line of the web divided by the flange width for Z section, or flange width minus the fastener distance from the center line of the web divided by the flange width. So we will have a parameter S, which is related to the fastener distance from the center line. T is the thickness of the channel or the web. B flange, the flange width. D is the depth of the channel. A gross is the gross area of the channel. So this case is not also in our course scope or in our project too, but if you have to design something similar to this, so you need to use clause 3.43 for weak axis member capacity. Okay, do you have any question, guys, up to here? So this is the first part of our lecture, and can we have a 10-minute break if you want? Do you want a break, guys? Okay, so we can have 10-minute break and we'll meet at 10:16. Thank you. Okay, so now let's have a quick example about the member under concentric load, axial compression load. Can you see the example? So in this case, we have a column under axial compression, concentric. If the load is in the centroid of the section, so this means the member is under concentric loaded. So we need to determine the maximum allowable axial compressive load for a C 250 section under the loading condition or under the condition of L equal to Lx equal to 6 meter, Ly equal to Iz equal to 3 meter. So the buckling lengths about X and Y are given, and our section is C 250 means the height of the member, and 1.19 1.9 millimeter is the thickness. So to find the maximum allowable load, we will need to calculate NS and NC. So let's start with the section capacity or NS. So N asterisk less than or equal to phi C NS. Phi C NS, phi C 0.85, NS is equal to A effective times F yield. So from Lysat tables for C250, 250 19, CL450. The grade is 450. So A effective is 381 millimeter, and F yield is 450 MBA. So this means that NS equal to 380 millimeter times 450 equal to 171 kilonewton. So N asterisk should be less than 0.85 times 171 equal to 14, 146. So our first condition in asterisk should be less than or equal to 146 kilonewton. So this from section capacity. For member capacity, we will need to find NC. So N asterisk should be less than or equal to phi C. NC, phi C is equal to 0.85 again. NC is equal to A effective times Fn. So our main target is a Fn, or the critical buckling stress. How can we find the critical buckling stress? We need lambda C. So if we go quickly back, so to find Fn, you need lambda C. To find lambda C, you need FOC. So that's why here, to find Fn, we need firstly to know how much is FOC. FOC, we have, as you know, three cases. The first case is flexural buckling, torsional buckling, and flexural torsional buckling. So if we look here, FOY is the flexural buckling stress equal to pi squared E LAY RY squared. So the first thing is we need to find RY. RY is equal to root IY over I over A. This if not in the table. If it is on the table, you can find the value directly from the table. So RY is 26.3. So this means that FOY equal to pi squared times E. E is 2 times 10 to the power 5, or 200 times 10 to the power 3. LEY, buckling strength about Y, given in the problem, buckling length about Y axis, 3 meter. So this one is 3 meter. All the units should be Newton and millimeter for consistency. So this is 3000 millimeter. RY 26.3. So we can find that FOY in this case is 159. So this is the first case of FOC, 159. But we will need to find the torsional and flexural torsional stress. Because no data or no given information that there is no torsional, or we prevent the torsional or flexural torsional buckling. So for the flexural torsional buckling, FOC in this case, or in the standard FOXZ, is equal to 1 over 2 beta FOX plus FOZ, and so on. So we need FOX, FOZ, and we need also beta. FOX is equal to pi squared E divided by LAX RX. From the table, Rx is equal to 97.1 millimeter. LAX given in the question is 6 meters, so 6000 millimeter. E, Young's modulus of steel, 2 times 10 to the power 5. So FOX is equal to 517 MBA. FOZ, what is FOZ? FOZ is the torsional buckling stress. So the torsional buckling stress formula is GJ divided by A gross RO1 squared 1 plus pi squared EIW divided by GJLEZ. G is the shear strength, shear modulus 80 times 10 to the power 3 MPa. A gross tables. J tables. E 2 times 10 to the power 5. IW tables. J table. LEZ is the buckling length about Z, which is given as 3000 millimeter. RO1 is the polar radius of gyration. If it is not given in the tables of LISAT, for example, or in the given directly, so you need to use the formula Rx squared plus Ry squared, XO squared, XYO squared. Rx and Ry, radius of gyration about X and Y. XO and YO is the location of CG. So for this section, the value of RO1 is 111.7 millimeter. So this means that everything now is ready to find FOZ, or the buckling, the shear, the torsional buckling stress, which is 157 MPa. So we can add one slide here. For this example, maybe it doesn't show directly. So for torsional buckling stress, we need to find FOZ. FOZ is 157 MPa. So if we compare, we have two cases now. We have flexural buckling and what? Torsional buckling. The flexural buckling give us 159 MPa, and the torsional buckling is giving us a stress of 157 MPa. So which one is critical from these two cases? The torsional buckling stress. But in this given example, because anyway we will need to find the flexural torsional buckling, so it didn't the example didn't show the details of FOZ as a separate case. But based on the explanation we have earlier, we have three cases. The first case is flexural buckling, the second case is the torsional buckling, and the third case is what we are doing now is the flexural torsional buckling. So we got FOZ. So now we know FOX, FOZ. So the last parameter we need to find now is what? Beta. So what is beta? Beta is equal to 1 minus XO divided by RO1 to the power 2. XO is CG location from y-axis, just from tables. RO1 is the radius of gyration, polar radius of gyration. So we got beta equal to 0.81. So now we can find FOC. FOC is equal to 1 over 2 beta FOX plus FOZ minus root FOX plus FOZ all squared minus 4 beta FOX FOZ. So finally we got that FOC or FOXZ in this case is 146. So FOC or the critical stress due to flexural torsional buckling is 146. So what does this mean based on what we have now? We have 159, 157, 146. This is case number 1, case number 2, case number 3. So the critical case would be this one here, which is from the flexural torsional buckling. So the next step will be find lambda c equal to root f yield over f OC. So this will be our next step. So after we got this case, so FOC is now 146. So now we can find lambda c, the slenderness ratio, equal to 1.75. More than 1.5. So this means that our Fn value is equal to 0.877 divided by lambda c squared all multiplied by F yield. So if we revise back or go back to the formula here, lambda c 1.76. So the formula here is 0.877 divided by lambda c squared multiplied by F yield. So we have already lambda c as 1.67 and we have F yield 450. So we got Fn or the critical stress for a member capacity is 127. So after we finish this step, we got Fn already as 127 MPa. So now we need to find Nc equal to A effective multiplied by Fn. But this not A effective from table at F yield because it is effective area at Fn, not at F yield. So how can we find A effective? So we need to calculate the effective area using the the process we have done before for effective area in close in this close here, the effective area lecture. It was the lecture before this before last week lecture. So section 2 is section probabilities. So effective widths of stiffened element So we will need to use this section to find the effective area. So we need to find firstly the slenderness ratio of the member, and then we decide if it is based on lambda. So we can find rho, then we know how much of the section or the area is effective and how much is not effective. So if we go back to our slide, so we will need to find lambda for whip and for flange to find A effective at Fn. Okay, so here we need to find A effective at F asterisk equal to 127 MBA, where B over T is equal to 240. So this for the web. For the web height is 240.2 and the thickness of the web is 1.9. So this distance, this ratio here, B over T, is 1 to 6. Okay, and now lambda is equal to 1.052 divided by root k multiplied by the effective stress multiplied by, sorry, the ratio B over T multiplied by root 127 divided by 200 times 10 to the power 3. So lambda in this case is 1.06, 1.67, sorry. And this means that rho is 0.52. Okay, and this means that B effective in this case will be rho times B. Okay, so this means that we lost 115 millimeter of the web due to the compression or the buckling of this web. Okay, so B effective in this case will be rho times B, where rho is 0.52. Okay, I just try to find the formula and the standard to show you. Do you have any question, guys, now? Okay, so this for the web. We need to do similar thing for the flange. So for flange, after calculation, I will jump on this one now. So after calculation, we found that B effective equal to rho B. Rho will be taken as 1 because lambda is 0.43 less than 0.67. So this means that B effective equal to B in this case. So no loose in flanges, or the flange are fully effective. So the flange in this case are fully effective. That's why we will consider the whole flange. And now we have the lips. The lips for this section, the depth is 11.6 millimeter. So lambda for this case will be 1.052 divided by root 0.43. We got it as well as 0.25. So lambda for the lips less than 0.67. So this means that rho for the lips equal to 1 as well. So lips are fully effective. So now only the web lost part of it due to buckling or due to compression. So area effective in this case will be the total area of the section, area gross, minus the lost area of the web. How much is the lost area of the web? We lost 115 millimeter length multiplied by 1.9 millimeter thickness. So this L and this T. So this means the effective area at Fn is equal to 808 minus 1.9 times 115 equal to 590 millimeter. So this means NC is equal to 0.4749. So N asterisk should be less than 0.637. So the section capacity was 146, sorry, and the member capacity is 63.7. So the maximum load is equal to 60, the smallest or the least value of both. So it is 63.7. So this was an example of the concentric loaded columns. And let's have a look on the members under combined loading. So if we have combined axial load and bending moment, we have two cases. One case for what? For combined axial tension and bending. So the first one is axial tension and bending. So we have N tension and moment. The second one is we have compressive axial load with bending. So we have N asterisk compression and moment. For the combined axial compression, the problem again is the buckling. So we have second order effect due to buckling. Okay, this part is covered in the standard under clause 3.5. So for 3.5, we have combined axial compression or tension and bending moment. 3.51 is the combined axial compression and bending. Okay, so let's go to our slides. So we have combined axial tension and bending, combined axial tension and compression. Sorry, combined axial tension and bending, combined axial compression and bending. So let's start with combined axial tension and bending. For the combined axial tension and bending, we have the cases we have two formulas here. We have m asterisk x over phi b phi bending mbx, and so this for moment about x, this for moment about y, and this for moment for the axial tension. So the combination, as you can see here, the main thing is here we have negative sign. So this for failure about failure of the compression flange. The other possible failure mode is yielding of the tension flange using this formula here, because this tension about tension of or yielding of tension flange. So we have three components of the formula as well. One for the axial tension and one for moment about x or moment about x axis, one for the moment about y axis. Okay, the main thing to consider here is here the two signs are positive because we are checking tension, failure of the flange. Here we have negative because we are checking what? The compression failure of the flange. Where this is the definition of the parameters here. MSXF and MSYF. This is section moment capacities, and both of them are equal to ZFT times F yield, where ZFT is the section modulus of the fall section for the extreme fiber about the relevant axis. Okay, so this means if you are calculating MSX, this will be ZX from the table. This one we are using ZY from the table. So here ZFT is equal to ZX or ZY. Sorry, ZFT is ZX or ZY based on X axis or Y axis. So this is for what? For axial tension and bending, because no buckling problem. So it is easier than the other case we will have now, which is Beam columns member under combined axial compression and bending. So for axial compression and bending, what is the problem? The buckling. So for the structure behavior of these members, the beam columns under axial compression and bending, the factors affecting our capacity or our design are shape and the dimension of the cross section, loading on the member, location of the applied eccentric load, member lengths, member and end restraints, bracing condition and spacing. So all these are the parameters that affect the overall buckling behavior of the members under N asterisk compression and M asterisk. And here in this slide, this is some of the cases of the member loads. So we can have extent to up to have the N and asterisk and M asterisk. We have several cases. One of them is applying eccentric load. Eccentric load means the load itself not applied at the CG or not applied at the centroid. What this mean? This means that you will convert this eccentric load to N and M. One option of bending is you have normal applied load, so this beam under bending moment due to the vertical load. And what else you applied? Transverse compression. So this is in asterisk. The third case is you have axial load plus end moment and shear due to like frame connection. If you have frame connection here, for example, like if this is a frame, so the column will transfer shear and moment to the beam. So this member or this member is a beam column because it is under N asterisk and M asterisk. Okay, so these are three cases of sources of bending and axial stresses on our members. The formulas that cover this part in the standard are these ones here. Close 3.51 and 3.52, sorry, 3.51.1 and 1, 2. So the standard give us these two cases here. For N asterisk to satisfy the combined action the combined action between compressive axial load and bending moment. So we have term for axial load for N asterisk, term for m axis and my. So this general formula, because in some cases we can have only n asterisk and m asterisk x only. So, but if you have asterisk, m asterisk, my, mx asterisk, and my asterisk, this is our formula. Okay? As you can see here, we have this parameter here, cmx and alpha nx. Okay? Alpha nx and alpha ny. So this for the second order effect. If you remember, for framing actions, we have second order effect, which means the effect of the buckling on the amplification of the moment due to buckling of the members. So this was also in the steel hot rod steel member, but maybe the parameter a little bit change it, but I mean same concept. We need to amplify the moments. So here we have amplified the moment due to buckling of the column under n asterisk. So we have two clauses, as you can see here. Two clauses for n asterisk. One of them using CAMX and m asterisk. Another one without the amplification. Both of them should be satisfied. Satisfied means both formulas should be less than or equal to 1. And all the signs are added together. Okay, the standard give us another limit, which is when n asterisk over phi nc less than 15. So this means we have small axial compression on the member. So in this case, we can only use this formula instead of the first two. So only this one. So in this one, we have n asterisk over phi c, nc, m asterisk over phi mb, mbx, m asterisk y divided by phi b, mby. And also again, should be less than or equal to 1. Okay, guys, I think that's enough for now. We can continue in the class. I will see you in the class. Thank you. Do you have any question before we leave?